Right, well, thank you very much. Thank you, Rebecca and Aaron. Aaron and Rebecca, you are heroes doing this stuff. Thank you, thank you, thank you. So I actually spent 2 years as a postdoc, actually 3 years as a postdoc in Austin, Texas. So it's great to come back, but I hadn't actually been back since then. It's crazy. And I was going to say, I have a lot of great memories of Austin, especially on 6th Street, but I think the more appropriate phrase is I actually lost a lot of great memories on 6th Street in Austin. But anyway, so now I am going to try and go over the first, a bit about Chandra and sort of celebrate the first 20 years. So thank you, everyone, for coming out to celebrate with us the first 20 years of Chandra, and I hope we have more than that. So Chandra here, of course, and an artist's impression, not a photograph. Some people do ask that. Is this a photograph? No, it's an artist's impression. Anyway, let's get on with it. So the first thing I thought I would go through was, what the heck is X-ray astronomy, right? I mean, some of you obviously know, but maybe some of you don't. So in 2 minutes, a really quick recap of how we got to be sort of studying stuff in X-rays and where it all came from. So the thing starts actually here with our own sun. How many of you saw totality in the 2017 eclipse? Oh, a good number. Excellent. Visceral, brilliant experience. For me, it was remarkable. The first one I actually saw, and seeing the solar corona here with my own eyes was just so emotional for me. It was fantastic. I actually study these on stars, so to see it on the sun was brilliant. Anyway, so back in about 1940, so, Swedish astronomers, Swedes, Hannes Alfvén and Bengt Eklund realized that some of the light coming from this diffuse corona was actually at 1,000,000 degrees Kelvin. They knew this because they saw some of the light from highly ionized iron, the iron with half of its electrons missing. And this only happens in a plasma of about 1,000,000 degrees. So this placed the temperature of the corona at 1,000,000 degrees. So our sun, 6,000 degrees or so, it sort of emits in the visible, as we see, right? As you bump up the temperature, the wavelength of light gets shorter and shorter and shorter until at 1,000,000 degrees, you're starting to emit in X-rays. So at this point in time, 1940, we knew the sun must be an X-ray emitter. And so then the race was on to actually observe it. But how do we do that? Because X-rays are sort of absorbed in the atmosphere. So in order to actually see the sun in X-rays, we need to go above the Earth's atmosphere. And of course, we couldn't really do that in 1940. So it actually happened in 1949. And how did we do it? Well, Herbert Fryman first did it with flying essentially a Geiger counter, the sort of thing that goes click, 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 click when it sees radiation. Flew a Geiger counter on a V2 rocket here. V2 rockets captured when the Allies overran the factory in Germany. So the sort of vilest instrument of mass destruction and war actually repurposed for science, which is, to me, is actually a brilliant thing that they actually did with that. It's actually fantastic. They captured enough to fly about 80 or so missions of science-oriented stuff with V2 rockets. So he first detected the sun in X-rays. Now, stepping forwards, 1962. So 1962, here we have Riccardo Giacconi, who was to later win the Nobel Prize in 2002 for the development of X-ray astronomy. So he actually flew an experiment, another Geiger counter on a rocket, to try and detect the solar X-rays that were scattered from the moon's surface. And so he launched this thing. Now, the thing about this experiment was there was no way in hell that it was actually sensitive enough to detect the moon. And I spoke to Riccardo Giacconi, and he actually knew this. Okay, so what was happening then? Anyway, so it launched, and here is again the sort of counts of the Geiger counter as it scanned in across this thing. Anyway, click, 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 past the moon. There was nothing really in the moon, but there was a whopping great source of X-rays somewhere in the constellation of Scorpius. Now, it couldn't locate it very well, so they just called it Scorpius X1 for short. It turned out to be later be a sort of a stellar mass black hole that's sort of eating its binary star companion. But that was the first detection of a celestial X-ray source. And so Riccardo said, okay, we need to build a telescope to see that. Oh, look, I said all that. I forgot to press my button. Okay, I won't forget this time. 1963, so Giacconi already in 63 had proposed an instrument, or at least sketched it out and waved it in front of NASA people, said, this is what we need to build to see all of these X-ray sources. We need something that's 30 feet long, and it has like a sort of meter-wide aperture at the front in order to do it all. And this is to try and observe sort of stars in X-rays like the sun with the same precision we can do with visible light telescopes. But of course, we couldn't really build this right then. No one had the technology to actually do this. So there were like several satellites and technology development sort of initiatives in that sort of stream before we actually got to Chandra. But this was when it was first conceived, after the first source of cosmic X-rays was discovered. And there we have Riccardo Giacconi, who's giving this seminar and has some very good respect for the no smoking rules of Stanford University, where he was actually giving that talk. Yes, so I can't really swear in astronomy. No, okay, no, I won't swear. No. Okay, so a lot of you are familiar with X-ray machines in hospitals, right? You go to get your bones X-rayed. How does that differ to an X-ray telescope? Well, essentially what you're doing with an X-ray machine in a hospital, you have this source of X-rays that's in the X-ray machine. It basically just passes through your hand and sort of, in the old days it was a photographic plate, but it's basically just a shadow. It just makes a shadow of what you put in front of it. An X-ray telescope instead, we actually have the source of X-rays. The source of X-rays is the universe. And what we're trying to do is to try and focus those onto a detector, which is now like a sort of same sort of detector that you have in your phones and cameras. Well, a little bit different, but the same principles. And you've noticed that I've drawn this focusing device here in a rather strange way. And that is because a normal mirror cannot focus X-rays. So here we have this it's an animation. It's like, I love it. It's like 1999, designed to sort of describe how Chandra mirrors work. So if you have a normal sort of mirror that optical astronomers use, like big telescopes, sort of reflecting telescopes have these big mirrors, X-rays just get absorbed by these mirrors. They don't reflect at all. In order to reflect and focus X-rays, you need to sort of fire the photon. These actually look more like photon torpedoes, actually, don't they? Anyway, so you fire the photon torpedoes at the mirror at a very sort of shallow grazing incidence, and Chandra is between 1.5 and 3 or so degrees. And then you are able to build a sufficiently accurate mirror to actually focus X-rays. So this is, so Chandra has these 4 nested shells, 4 of these mirrors. These are sort of called grazing incidence optics that were devised for X-ray astronomy. Oh, okay, and here we have it. So this is Chandra's, one of the sets of Chandra's mirrors. Chandra's mirrors are both the smoothest mirrors ever built, and also probably the most expensive. These mirrors cost $500 million just to build the mirrors, and that's $1990. So these are terrifically difficult to make and very expensive. So very, very smooth. So to put that in context, if they were the size of the Earth, then the biggest mountain on the mirror would be about my sort of shoulder height. So extremely smooth, extremely well polished, and they have to be that way, otherwise they wouldn't reflect the X-rays very well. They would just scatter them in random directions. So once we built the mirrors, then we have to build the rest of the satellite. Every time I look at this photo, I can't help thinking that this chappie here is like sitting in a $1 billion hot tub. So this is like the satellite bus, what we call it, the bit in this part here that controls essentially all of what Chandra does. This is the shake test for this thing. So when you build a satellite, you have to you have to shake it all and test to see whether it destroys itself or whether it will actually survive the rigors of a launch and all the vibrations and stuff. So this was a shake test, and thankfully everything didn't fall to pieces. It has happened on certain satellites. But Chandra survived, and Chandra was built, and then that takes us to
12, 11, 10, 9, 8, 7, 6, 5, 4, 3. We have a go for engine start, 0. We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
Columbia is in the roll. We've got a fuel cell pH number 1.
Roger, roll, Columbia. We're looking in.
Every time I see that, I still get goosebumps. It was just if you've ever seen a shuttle launch, you'll know, but it's just a very emotional, very visceral, especially when your telescope's sitting on there, and you know that if something goes wrong, not only is it tragic for everyone, but also the telescope is gone. It's a really, really emotional experience. So you would have maybe heard there. So it's not only reaching new heights for X-ray astronomy, but also for women. And the reason for that is that, the commander for that shuttle mission, STS-93, was one only Eileen Collins, the first woman to have commanded a shuttle mission. And this is taken in the shuttle 0G, and you see her hair all over the place in 0G. And this is our mission banner in the background with Chandra written on it. So Chandra was originally called AXAF, which stood for the Advanced X-ray Astrophysics Facility. That really rolls off the tongue nicely, doesn't it? So it was actually renamed after, as most satellites are. It was actually renamed just before launch, but it was renamed for this chappie here. Subramanian Chandra Sekhar. He was an absolute giant of astrophysics of the 20th century. Did lots of work that was actually foundational for things that are really important for X-ray astronomy. So a very appropriate name for Chandra Sekhar. Born in India, went through the UK and came to work in the University of Chicago. Okay, so Chandra gets launched. It's up there. Now, it's in low Earth orbit, Space Shuttle's low Earth orbit, and it needs to get boosted to a much higher orbit, and then it needs to have checkout. We need to sort of unfold the solar panels, and all that stuff takes about 3 weeks. But, there's every step of the way, something can go wrong, and it's just like, it's like nerve-wracking for 3 whole weeks, where every little thing could, ruin everything. But eventually we got to the point where everything checked out, and we got to the point where we had to open the sunshade door. And that was 12th of August, 1999. And here we all are. And I don't know why, but we were packed into the tiniest room in the sort of Chandra control center there, where the data feed was going to come in when we opened the sunshade door. So this was actually the last piece of hardware between the X-rays from the universe and our detectors in Chandra. And we were going to open that, and we did. And then we had to sort of wait because it took a while for the data to accumulate and for things. It's like X-rays, there's a lot less of them around than there are optical photons. It's not like just like you take a quick picture and there it is. You actually have to wait a while for everything to integrate. And we were sort of, so there's me in the background there. I don't look really any different to what I do today, but and there's all sorts of thoughts sort of racing through your head like, oh my God, is it going to work? What's going to happen? And as somebody said, well, maybe we're just flying a bucket full of broken glass right now. All that sort of thing. And then, the thoughts like, why the heck didn't I shave and get a haircut for this historic photograph? But eventually, the data appeared, and we started seeing photons, which is great. And what this is Marty Weisskopf, Marshall Space Flight Center, the project scientist, was pointing at right at that moment was this thing here. So this thing here, we didn't know where in the sky we were pointing at this point. We didn't know what bit of we know roughly, but we didn't know where we were. And so we didn't know what the heck this was, but it's a cosmic source of X-rays. And the fact that it was the right size, it was 2 arcseconds across, that meant that everything was working great. We weren't focused yet, but we were close enough. So this was like a huge relief when we saw that. It was just fantastic sort of feeling to see that finally work. Okay, so now we've got a telescope in orbit. What do we actually do with it? Well, let's step back in time to, let's say, 1572. So this fellow here, Tycho Brahe, and yes, he is the chappie with the brass nose, yes. He actually lost half his nose in a sword fight with a colleague. And, the sword fight wasn't about, it wasn't over a woman or over money or anything. It was actually over who was the best mathematician. Yeah, so that's brilliant. So he noticed a new star in the sky in the constellation of Cassiopeia that gradually faded over a period of about 2 years. 2 years, and then it was basically gone. Now, if you look at that part of the sky right now, today, that's what we see. That's where Tycho's star was, right in the middle of that field of view. Now, we look at it with Chandra, and that's what we see. So this is actually, of course, a supernova event. It's now called the Tycho supernova. And this is the Chandra image. Now, the colors here are all false colors. So, we can measure X-ray colors, but red, it's a sort of redder X-ray than the blue, but we just all make up the color tables. So these are sort of arbitrary, and this is sort of shown in the next one where, wow, look, we just flip it completely, and now it's mostly yellow. But the thing is that we can see actually this supernova remnant expanding now. So this is like a ball of like million-degree gas or multi-million-degree gas, all sort of expanding from an explosion, just like it looks like, with lots of detail that gives us insights into how the explosion works. And now if we sort of flipping back between 2000, you can actually see the thing expand and measure how that blast wave or that sort of remnant is going. Again, very important to understand the energetics of the explosion. Jupiter. Okay, so I've been telling you that X-rays come from really hot cosmic sources, really energetic things. what the heck is Jupiter doing here? You know, Jupiter's got a temperature of about minus 145 centigrade, which is, as I was thinking this morning, is about the same temperature as the air conditioning in my hotel. But when you point an Xray telescope, when you point Chandra at Jupiter, you see this. Whoa. Now, I'm sure like half of you are saying, oh, I know what that is. And you're right. This is, of course, the aurorae of Jupiter, right? This is the aurorae. It's in the poles of the planet. But Jupiter's aurorae are not like the Earth's aurorae. Well, they're a little bit like it. But Jupiter's aurorae have this weird source of aurorae-ness. And this is Io. This is a Juno picture of Io. So the gas that plummets down onto the surface of Jupiter actually comes from volcanoes in Io. So we are, with Chandra, we are seeing gases from the volcanoes of Io precipitating down onto the poles of Jupiter, down its magnetic fields. I mean, just it's absolutely staggering. And these things actually have an oscillation of about 45 minutes. They sort of pulsate. And nobody really understands that quite yet. But these observations with Chandra and with other satellites are really sort of giving us a great insight into how these things actually work. And we know it's Io because we see light from sulfur ions in here from the volcanoes. It's just actually staggering. Okay, so I think do I have time for last? Yes, okay, right. So I spent, all this time saying, well, Chandra's not like an X-ray machine. But Chandra we actually did use it like an X-ray machine. It was back in 2003. And it all starts again with another one of these 1054, back in time things. Okay, 1054, you know where this is going. This time it was Chinese astronomers noticed one of these new stars in the sky. And what was it? Well, it turns out to be this thing, the Crab Nebula, that many of you would have heard of. And you can actually see this thing in your backyard with a telescope, right? You can see the Crab Nebula. Chandra's view of the Crab Nebula looks like this. It's like this sort of giant X-ray Catherine wheel of emission, powered by this neutron star in the middle, which has a phenomenally strong magnetic field, and it's rotating wickedly fast. So we have this sort of diffuse source of X-rays. Now, you know that planets, of course, move relative to the stars, which is how they were, of course, found to be planets and not normal stars. It turns out that every several hundred years, Saturn actually goes across the Crab Nebula. Okay, so, when would this, every several hundred years? Well, when would this have happened? It turned out in 2003. Okay, 2003. But we'd missed Saturn. Saturn went past while Chandra was in a bad part of his orbit. We couldn't observe. But we caught this fellow here. So this is Titan, Saturn's largest moon, Titan. Okay, so Titan actually traversed the Crab Nebula and sort of did something like this over a period of several hours. And so what we're able to do now then, this is our cosmic X-ray machine. This is that sort of the source of X-rays. It's the hospital X-ray machine. This is your hand in front of it. And now we can measure we can see what the image of that. We can measure the shadow of Titan. Now remember I told you that X-rays don't sort of penetrate atmospheres. Atmospheres are too thick for the X-rays to penetrate. So this shadow is not the sort of optical surface, the visible light surface of the star. This is actually a bit bigger. This is the star plus atmosphere. And so we can actually use this shadow to measure the height of the atmosphere of Titan. So I really want, before I sort of hand over to my colleague and friend Dave Pooley to sort of do the rest of the universe, I just wanted to, end on this sort of note that X-ray astronomy now, we used an exploded star that the Chinese observed, which is now an X-ray emitting remnant, and we used a transit of the bloody moon of Titan across this X-ray remnant to measure its atmosphere. It's just the breadth of X-ray astronomy and the physics that we learn from X-ray astronomy today is just absolutely staggering, absolutely mind-blowing, which is why why we get up every morning and do it. Absolutely phenomenal. And Chandra has brought us a lot of this progress. So I, cringy use of Winston Churchill phrase, but he had all the best quotations. And I'll probably get it wrong, but the phrase was, and this I think applies to Chandra. So it's not yet the end, because Chandra first of all has at least another 10 years, I hope. It's not even the beginning of the end, but this Chandra, I think, maybe when it's all said and done, will be the end of the beginning. Thanks very much for listening, everybody, and thank you.
Thank you so much, Dr. Drakester. We have time for a couple questions. If you want to ask a question, raise your hand. I will call on you after you ask the question. Hopefully one of us will remember to repeat the question, and then Dr. Drakester will respond. All right. How about we start right here?
Are the mirrors made of any special material?
Yeah, the question was, are the mirrors made of any special material? Yes, they are. They're made of a special glass, and so the first sort of X-ray mirrors that were flown in space were made of metal, but you can't really get a really good polish on metal to the precision that we need for X-ray optics for Chandra's sort of design. So yes, they're made of glass, but they have to be. So X-rays reflect off materials like glass at a very shallow angle. But you can increase the efficiency of that if you also coat the mirror in a sort of high, what we call high Z element, so a heavy element like gold or in the case of Chandra's mirrors, they're coated in iridium.
Interesting. There in the back.
The question was why 4? Why does Chandra have 4 shells? The bottom line for that answer is essentially money. So Chandra's mirrors are quite heavy, and basically it boils down to what is the budget in your spacecraft for mass, and how much mass can you fly. And for the way that these mirrors work, the way they design, they have a certain mass per shell. So that sort of defines how many shells you can have. Now, I will point out to you that there is a bit of a gap in here. So there's an inner shell and another inner shell, and there's a gap and two outer shells. This gap actually was originally to be filled by 2 other mirror shells. It should have been 6. But Chandra went through a little bit of a cost-saving. So, I said these were $500,000 just to build these 4 shells. So Chandra went through a cost-saving cut, and one of the D-scopes that we had was to get rid of a couple of the shells, and so that's why we have only 4. Now, more modern telescopes, like the next generation, we're going to be building the mirrors much thinner, and then we're going to have loads more shells. But at the time, and I think still today, the best way to get a really precise X-ray telescope is thicker mirrors made of glass, and that limits the number you can actually fly.
All right, we might have time for one more question. How about you right there?
I was wondering, how fast do X-rays travel? Like, you can see light travel, you can see back in time. Is it the same with X-rays?
So the question was, yes, how fast do X-rays travel? Yes, X-rays travel at the same speed as visible light. So all electromagnetic waves, they will travel at the same speed. So when we see things with X-rays, we see them with an optical telescope at the same time. Imagine you pointing both telescopes, visible light telescope, X-ray telescope. We're seeing that light coming from the object at exactly the same time.
All right, we have a couple good other questions. Hopefully Jeremy will be around during intermission.
I will, yes.
Yeah, so make sure you find him if you have some more pressing questions asked. Let's give him another round of applause.
Thank you.